In this video, we will give further examples of how to use Vsepr theory to predict the shapes of various molecules. In this example, we have aluminum trichloride. Aluminum trichloride has the formula containing 1 aluminum and 3 chlorines. If we draw out the Lewis dot structure, we find that the aluminum violates the octet rule, but that's acceptable. It's right underneath boron, fairly ionic, so not that unusual a situation. And so in this case, we have to determine how many electron pairs there are surrounding that central atom, the aluminum. And so in this case, the central atom has 3 electron pairs, which then goes to the corners of an equilateral triangle and therefore has an angle of 120 degrees between the lone pairs, the central atom, and another lone pair. In order to predict the molecular shape of this compound, we have to recognize that the electron pairs that are surrounding the central atom are bonding pairs of electrons and are used to connect the aluminum to the chlorine atoms. And so this particular molecule has a trigonal planar structure, and it is got the angle of 120 degrees for the chlorine aluminum to chlorine bond angle. As another example, we can take a look at sulfur dioxide. Sulfur dioxide has a Lewis dot structure as shown here. By having double bonds between the sulfur and both oxygens, we do violate the octet, but this is acceptable since sulfur is in the third period. However, the other resonance structure, or the other structure that would be possible, would be a double bond to one of the oxygens and a single bond to the other, and this would require resonance structures. So this structure that you see here produces the lowest formal charges for all the atoms involved, and so represents probably the best Lewis dot structure. In this case, we see that there are 3 electron regions around the sulfur. In this case, the 2 double bonds between the sulfur and the oxygen are representing 2 electron regions, and then the 3rd electron region is from the lone pair on the sulfur. So again, we have a trigonal planar electron geometry, and this again produces a structure where the angle is going to be 120 degrees. What's a little bit different in this example is that only 2 of the 3 positions in the trigonal planar structure represent bonding regions. The 3rd is a lone pair. So in this particular case, then, the structure is not described as a trigonal planar structure, but is described as a bent structure, in which the angle between the oxygen, the sulfur, and the other oxygen is approximately 120 degrees. The 3rd position of the trigonal planar structure, of course, is occupied by the so-called lone pair. So this brings us to the point where we can summarize the possibilities for a structure that has 3 electron regions around the central atom. The first example is when all 3 of the positions are bonding between the central atom and the terminal atoms, as in Bf3. This produces a molecular structure that we describe as being trigonal planar, and of course the angle is 120 degrees. The second kind of structure is where there are 2 bonding regions and 1 lone pair. In this case, the overall electron pair geometry is again trigonal planar, but the molecular geometry is described as being bent with an angle of 120 degrees. This is our example for sulfur dioxide. If we continue to add electron regions, we can then examine something such as methane, CH4. In this particular case, if we take and draw out the Lewis dot structure, we find that there are 4 electron regions around the central carbon atom. The hydrogens, of course, only need 2 electrons to complete its valence shell. So in this case, the Lewis dot structure is shown here. If we then remember that with 4 electron regions, the optimal structure is a tetrahedral structure in which all of the angles are 109 degrees, or 109.5. And so in this particular case, then, we say that the electron geometry is tetrahedral. Since all 4 of those electron positions are bonding, we then say that the molecular geometry is tetrahedral as well. As an example of another situation involving 4 electron regions, we can look at something like ammonia, NH3. And so NH3 has a Lewis dot structure as shown here, where in this case we have 3 bonds between the nitrogen and the 3 hydrogens, but also the nitrogen has a lone pair. So again, the electron regions, there are 4 electron regions, so we have a base structure of the tetrahedron, again with 109.5 degree angles. But in this particular case, the one remaining position in the tetrahedron is occupied by a lone pair, and so in this case, the electron geometry is, while it is a tetrahedron, the molecular geometry is described as a trigonal pyramid, where the 3 hydrogens form an equilateral triangle and the nitrogen is in a position which is above that equilateral triangle and therefore forms a pyramid. The angles in this molecular geometry, of course, are 109.5 approximately. We can take this a little bit further and look at a molecule such as water. In this particular case, the Lewis dot structure has the structure shown here, where there are 2 bonds between the oxygen and the 2 different hydrogens, but now we have 2 lone pairs. Again, there are 4 electron regions, 2 of them being bonding and 2 of them being lone pairs. So the electron geometry is again a tetrahedron with angles of 109.5. But the situation for the molecular geometry is described as being bent. The angle between the H, the O, and the H is again approximately 109.5 degrees. So to summarize the possibility when there are 4 electron regions, if all 4 of the electron regions around the central atom are bonding, we have a tetrahedral molecular shape. The angles are all 109.5 degrees. This is a good example of methane, but there are many other examples. If we had 3 bonding regions and 1 lone pair, as there is in ammonia, then we describe the molecular shape as being a trigonal pyramid. The angles, again, are all approximately 109.5. And then the final example is where we have something like water, where there are 2 bonding regions and 2 lone pairs. And so in this case, the molecular shape is described as being bent, and again with an angle of 109.5 degrees.